Here is the final Math 117 sample problems video for class 25. First problem is a slightly messy but interesting calculation. You now know that the first term in the Black-Scholes equation can be interpreted as the current share price times the fraction of a share that you need to know in order to hedge your position. You also know that the first term can be interpreted as an expectation. It's the expected value of a contract that lets you get one share of the underlying security if the price on the maturity date exceeds the strike price. Here's a final interpretation. We're going to interpret this as the probability of some event. And since you multiply the share price by some number between 0 and 1, this has to be the probability of something. So what's interesting is the formula for what it's the probability of turns out to be quite simple. So let's write down what we've got. I got this. Theta sub t. That's the thing that gets multiplied by the share price. And this is the function capital N. That's the distribution function for the standard normal distribution, evaluated for this function that Deneen and we have been calling lowercase g. So we can say, being the distribution function for a normal distribution, it's the probability of the event, random variable y, is less than or equal to the log of share price over strike price plus this rather mysterious r plus sigma squared over 2 times the time remaining until maturity, all divided by the volatility sigma times the square root of the time to maturity. But now think about the standard normal distribution. The density function is symmetric. There's the probability that the standard normal random variable is less than or equal to some a, here shown for convenience as negative, and by symmetry that's equal to the probability that this random variable is greater than or equal to minus a. So we have an immediate rewrite. This is also the probability that y is greater than or equal to the negation of what we had. I'm going to negate the logarithm by flipping over the ratio. Negate the second term. The denominator stays exactly the same. Okay, now what we want to do is eventually to isolate the share price at maturity on the left-hand side. And as a first step in accomplishing that, what I'm going to do is multiply through both sides of the inequality by this positive quantity, sigma times the square root of capital T minus little t. And that, of course, is going to be greater than or equal to the log of the price ratio minus r plus sigma squared over 2 times capital T minus little t. Well, we're making progress. Now, since the exponential function is monotone, I can exponentiate both sides without changing the inequality. So I now have the exponential of random variable y times sigma times the square root of the time to maturity has to be greater than or equal to. I'm conveniently exponentiating a logarithm, and I am exponentiating, and I'm going to split this up now, r times capital T minus little t minus sigma squared over 2 times capital T minus little t. Now comes the cute step. I am going to multiply through by x sub t. I'm going to move the factor involving the interest rate over to the left-hand side. And then, because I want a minus sigma squared over 2 in my exponent, I'm going to put in an e to the minus sigma squared over 2 times capital T minus little t. And I've still got my e to the y times sigma times the square root of the time to maturity. And that's greater than or equal to k. But now what did I do? I actually needed to multiply both sides by the factor e to the minus sigma squared over 2 times t minus t. So I now, on the right-hand side, have e to the minus sigma squared times capital T minus little t without the 2 in the denominator. And on the other side, I correctly have a minus sigma squared over 2. Why did I do that? Well, what is this? This is the price at the current time little t, multiplied by a factor that takes the interest rate into account, multiplied by the factor that makes the undiscounted share price a martingale, multiplied by the effect of the random variation. This is precisely the price on the maturity date, and that has to be greater than or equal to the strike price, discounted in a rather strange way, multiplied by e to the minus sigma squared times capital T minus little t. The advantage of having done this is we now have 3 interpretations for each term in the Black-Scholes equation, either as a probability or as an expectation or as part of a hedging portfolio. The next problem is a lot of messy arithmetic, and this is best done on a computer, and it's done in its entirety in the R script black-scholes-hedge.r, but I'm going to write out the summary of the results here so that you understand exactly what's going on. So, you've sold this Acme call option, and you realize you're going to be in trouble if the shares go up and the person who bought the option from you exercises it. So you hedge your position. How do you hedge your position? You hedge your position by buying a fractional share of Acme, which will benefit you if the price goes up. And in order to do this, you need to supplement the amount you got by selling the option with a bank loan, which is a fraction of the discounted strike price. Since if you are in trouble on this option, if it gets exercised, the option holder is going to pay you the strike price. The bank will have no problems with loaning you a fraction of the discounted strike price. So, how do we do this hedge exactly? Well, let's look at the first term in the Black-Scholes formula. We've got the log of 25 over 26 plus r, which is 0.04, plus sigma squared over 2, which is 0.02, multiplied by 1 year to maturity. And we also know that sigma times the square root of t minus little t is equal to 0.2. And therefore, if you look at the statement of the problem, we need to evaluate the standard normal distribution function on log of 25/26 plus 0.06 divided by 0.2. And when I worked that out, I got 0.5413. So that means what we want to do is to hold 0.5413 shares of Acme. Next, when we calculate R minus sigma squared over 2 times t minus t, we get 0.04 again, this time minus 0.02 or 0.02, and that's why I give you the value of the log of 25/26 plus 0.02 divided by 0.2. That works out to 0.4617. And what does that mean? That's the fraction of the discounted share price we should borrow. So you go to your banker and you say, you've already agreed that you'd be willing to loan me up to the discounted share price of $24.98, but I don't want that full loan. I'd only like to borrow 46.17% of that amount. So I borrow $11.54. Why is this reasonable? Because when I take the current value of the shares and multiply by the fraction of one share that I own, and then subtract off from that the amount that I now owe the bank, I get 1.9945, and this is very close to the current option value, which is a tad over $2. The difference between these is just due to round-off errors. And on the computer, when I do this in R, I don't round to 4 digits, and they come out exactly the same. Okay, so now you know how to create a hedging portfolio, but in order to get that hedging portfolio, I need all the raw data that went into the Black-Scholes formula, and in the real world, I don't have that available. So how do they do it in the real world? They say, if you differentiate the option value at time t with respect to the share price at time t, then it turns out this derivative is precisely equal to the number of shares that you need to own. This is a curious calculation because when you look at the Black-Scholes formula, you see that the share price shows up in 3 different places, and it turns out that 2 of the places, when you take the derivative and use the chain rule, the 2 terms cancel one another out. So you get this very simple result. And I've given you enough data to compute this. I say if the share price increases by 1/10 of a dollar, the option value increases to $2.549 from $2.004. So that's my estimate of the derivative, 0.545, and that is close to the fraction of a share that I need to own, which was 0.5413. The reason these are not exactly the same is partly round off, but partly because I approximated a derivative by a finite difference. Well, now all we need to do is figure out how much money we need to borrow, and the way you can do that is by estimating the derivative of the option price with respect to the strike price. In fact, my estimate is the negative of this derivative, so I say the option's now worth just a bit more than $2. If the strike price went up, of course, the option would be worth less. It would drop down to $1.95 and change. I take that change in the option price. That would result from a mere tenth of a dollar increase in the share price, and I get 0.441, and that is pretty close to the fraction of the discounted share price that I need to borrow. So this is apparently how financial engineers work, by looking at option values for different strike prices. That's the sort of data that's fairly easy to get. They can figure out the correct contents of a hedging portfolio. Now, in the Black-Scholes formula, which unfortunately doesn't fit on this slide, there is a square root of capital T minus little t in the denominator. And you say, oh, what's going to happen in the limit where little t approaches capital T? So these are a couple of steps in answering that question, and I've carried it a little bit further in the R script. So what happened? We sold an Acme Corporation call option with a maturity of 1 year. Strike price was 26 at a time when the share price was 25. And you'll recall we immediately hedged our position by going to the bank, borrowing slightly more than half of the discounted strike price. That, combined with what the option buyer paid us, was enough funds so that we could buy 46% of a share of Acme. Now, 6 months have passed, and in those 6 months, the price of Acme has gone up from 25 to 26. This is looking good for the person that bought the option. It's already up to the strike price. The discounted strike price has also gone up a bit because it now only has 6 months to accrue interest. And when I plug into the Black-Scholes formula, you will notice that the argument to n doesn't include the logarithm of anything. That's because the strike price and share price happen both to be 26, and the log of 1 is 0. So what do? We now need to own a larger fraction of a share. We need to own 0.5839 of a share, and in order to do this, we needed to increase our loan to about 53% of the strike price, and I can check that this is all consistent. I say, now I have a portfolio consisting of that fraction of a share of Acme times that share price. But in order to acquire that, I not only had to use the proceeds from having sold the option, I needed to go to the bank and say, I would like to borrow 0.5281 of the amount you've agreed it's safe for you to lend me, namely the current value of the discounted share price. So that's the discounted strike price. I said that wrong. And here's the fraction of that I'm going to borrow. And when I combine those numbers, I say I own a fractional share worth $15.18. I, however, have had to borrow $13.46 in order to acquire that. So I'm to the good by 1.72. That is precisely the current value of the option. So I am maintaining a portfolio consisting of a fractional share and a bank loan, which always has exactly the same value as what the option is worth according to the Black-Scholes formula. Okay, now we'll go on to step B. Another 3 months. We're now only 3 months away from maturity, and Acme's doing nicely. It is up to 27, $1 higher than the strike price. It's looking as though it's going to end up in the money. Furthermore, the discounting effect on the strike price is even smaller. The discounted strike price is now getting very close to 26. Again, I plug into the Black-Scholes formula. I have a smaller time to maturity. I have a ratio of strike price and share price that's different than it was before. And by doing the same old calculation, best done on a computer, I now need to own 70% of a share, which is worth $27, and I need to borrow a larger fraction of the strike price, so what is this portfolio worth? Well, here's my check. I say my portfolio consists of 0.701 shares of Acme, now priced at 27, but I have borrowed 66.54% of the discounted strike price. That you can see is now getting very close to 26. And when I work that out, I discover the net value of this portfolio is $1.80, which is consistent with the current option value, which is about $1.79. You can see why this option value is fairly low, even though the option is looking as though it's going to be in the money. It's going to be in the money, but it's unlikely that the share price will be significantly greater than the strike price. Okay, what's going to happen if we take this to the limit? Well, you can see I've been owning a larger and larger fraction of a share, and if Acme continues to do well and I discover that this option is going to be in the money, I want to end up owning exactly one Acme share. In order to do that, I'm going to have to keep borrowing more money from the bank. But what am I going to borrow? I'm going to borrow 100% of the undiscounted strike price. So when the option is in the money on the maturity date, here's what I do. I go to the option holder and say, here's that share of Acme I promised you. I turn over the share that I'm holding in my portfolio. The option holder says, fine, here's the strike price for it. That was our deal. I take that strike price, I walk to the bank and say, here's exactly the amount that I owe you, and I have come out even. Of course, if the option ends up not in the money, my portfolio is going to evolve quite differently. I'm going to start selling off my fractional shares of Acme. I'm going to use the proceeds from that to pay off the bank loan, and on the maturity date, I will own no Acme shares and I will own nothing to the bank. So in either case, I come out breaking even.